So I'll start now. So welcome everybody to our third week of the problem solving session. If you have already attended the third class, the week in the third class, then the problems will be mostly related to that. Okay, so our first problem being, calculate the wavelength of the lowest energy line in the Lyman series to three significant figures. In what region of the electromagnetic spectrum does it occur? So I'll give you 5 minutes. Please try to solve and let me know how are you approaching this problem and what answer are you getting. I hope everybody can hear me, right? Am I loud and clear?
Yes, ma'am.
Okay, then please continue. Now, what do you mean by lowest energy line? So how do you approach it? Do you all know how to solve this? Please let me know that. Okay, so 5 minutes up. Uh, you know that in the hydrogen on the electromagnetic spectrum, we have some lines like this, right? Yes, Anurag. You have to use a formula, but Did you solve it? What's the answer? And which region of the electromagnetic spectrum does this occur? Can you tell me that? So you have your energy lines like this, right? Or n is equal to 1, 2, 3, 4, and infinity. Now you know that as an electron is close to this, n is equal to 1. That means it's just in front of the nucleus. Yes, Dr. Nathucha, yes. So, and you know that as an electron moves away from the nucleus, it's in this region, right? So here that means electron is practically free for n is equal to infinity. Here our energies are discrete, and here we have continuum. Isn't it? So all the lines which fall on the n is equal to 1 orbit, this is the Lyman series. N is equal to 2, this is the Balmer series. Etc. and so forth. So what do you mean by the lowest energy line in the Lyman series? That means we're talking about this line, because you can see from the gap that the energy of this particular line will be the lowest, right? So we can use the formula. So we'll use the formula 1 by lambda is equal to RH, the Rydberg constant, 1 by n1 square minus 1 by n2 square. Okay, so you put in the values. So what do you get? The value which I have here is somewhat around 8.228 into 10 raised to the power minus 6 meter inverse. But this is 1 by lambda, of course. So now how will you get the energy? We have frequency. This is it, right? Okay, just invert this and you'll get something around 122 nanometers. So if you have got something around this, then it's perfectly all right. And as you can see, this is in the UV region of the spectrum. Now, what is the significance of this particular problem? Is it just a random problem? Does anybody know that? Well, let me tell you. This particular line is called the, yes, somebody wants to say something, is called the Lyman alpha line, and this is the strongest emission in the sun. Okay, it is this particular line which ionizes all the hydrogen and oxygen, okay, in the stratosphere. So we have the stratosphere, we have continuous breaking down of the oxygen molecule because of this particular line. Okay. Okay, so let's go to the next problem. This is also similar. So how many discrete spectral lines are possible for transitions from the n is equal to 3 to n is equal to 2 lines? It is similar, but you will see they're talking about the fine structure. Okay, so how would you go about that? Please think for a while and let me know. Anybody get the answer? Please think again. It is not 2. Okay, so you see, for n is equal to 2, you have 2 lines. Okay, one is the k is equal to 1 line, and k is equal to 2 line. And for n is equal to, you see, we are talking about the fine structure of the hydrogen atom. Okay, not just n is equal to 1 and you have got, not just n is equal to 1 and you've got one line, not one orbit. We are talking about the fine structure over here. That means because of the electronic spin, okay, because of the interactions of the different electrons in the different suborbitals, there is splitting in each of these levels, right? Here we'll just limit ourselves to the first split, like we are not talking about spin splitting about. So for n is equal to 3, we have 3 lines. And our selection rule for transition of electrons, what is that? Plus minus 1. Okay, so that means an electron can come down from 3 to 2. Yes. Okay, electron can come down from this line to this line. Yes, but it cannot come down from, and this, from a 2 to k is equal to 2, and then even if they are in different principal orbital numbers. Okay, this is not allowed. Okay, so again we can have a transition from this to this. Again, this is not allowed because then del k is more than 1. So how many lines do we have? 3 spectral lines. This is just coming from the selection rule, as depicted in the Bohr-Sommerfeld theory. Okay. Here we did not yet come into quantum mechanics, which will make all this even more precise, and there will be even further splitting. So yes, we have 3 spectral lines for this case. Is that okay? Okay, so let's go to the next problem. How do you calculate the ionization energy of a hydrogen atom in its ground state? We all know that it's something around 13 point something, right? But how do you get that? Can you tell me? So how do you get this? Can anybody tell me? Okay, so since we are talking about the ground state, that means we are talking about some transitions taking place in the Lyman series, isn't that? And this ionization of hydrogen atom, that means you basically want to take out the only electron which hydrogen has from its ground state, you want to take it out of the atom. So, as obvious, first we will just calculate the energy which is required to take one atom out of, sorry, one electron out of one hydrogen atom. So we have just solved that this equal to the constant, and here this is n is infinite, right? So what do you get if we substitute the values? Okay, okay, 1 by n infinity, you can say that it'll go to 0. So our equation is reduced to just RH by this. Basically just RH, the Rydberg constant. And what is that? 9.116. Okay. Sorry, this is here. I'll just write the value for RH. That was the into 10 raised to the power 7. Right? This, you divide it and you get 116 into 10 raised to the power minus 8 meters. So the wavelength uh, so this is just the wavelength associated with this particular transition. I think I have some issue. I'll turn off my video. Okay. Okay, so this is the wavelength, right, associated with this particular transition. Now, in order to find the energy that corresponds to this transition, we need the frequency, right? We need the frequency nu of the photon that is emitted when this transition takes place, like if the electron comes down to the ground state. Okay, so you know that the associated equation is this, and you solve this to get, you put the value of lambda and c, and you get nu is equal to c by lambda ten raised to the power 8 meter per second by this 116 into 10 raised to the power minus 8 meters. Okay, so this will give you the answer, which I have here is 3.291 into 10 raised to the power 15 per second. Okay, or you can say hertz, but that unit is not required here. And so from Planck's equation, you know that energy E is equal to h nu. Plug in the value of h, which is Planck's constant, 6.626 into 10 raised to the power minus 34, and whatever value of frequency that we have got, 3.291 multiplied by 10 raised to the power 15. So this comes out to be something around 2.181 into 10 raised to the power minus 18 joule. Okay, so this is the energy associated with this particular transition. If we have one electron in the hydrogen atom and we want to take that particular electron out from the single atom. Uh, but what we need here is the ionization energy. Okay, whatever we have here, let us write that down in the form of a gist, that you have hydrogen in the gaseous state and you supply it an energy of this to whatever we've got into 10 raised to the power minus 18 joule, and this gives you our ionized hydrogen atom. You have the electron out. Okay, but the ionization energy, this implies that we need the energy which is required to remove, let me just write it here, ionization energy. This is the energy required to remove 1 mole of electrons from 1 mole of hydrogen atoms in the gaseous state. Okay, so that means we have to use, when you see all these terms, moles, 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 you need to use the Avogadro number. Okay, so therefore, to convert this energy to kilojoules per mole, we'll again use another fact that 1 mole of photons contains the Avogadro number of photons. Okay, so finally what we end up with is therefore the ionization energy is given by, you write the Avogadro number multiplied by the energy that we have got. So this is supposed to give you 1313 kilojoule per mole. Okay, but you will see that the value of this energy cited in literature is around 1312 kilojoule per mole. Literature says that, but probably this is because we have used, made an estimation of the Avogadro number. I mean, not the exact energy, but because of this number, basically, we have rounded off the Avogadro's constant. That is why. Is that okay? So I'm just writing the assumption, or the discrepancy. It's not an assumption, I'm just writing rounded off Avogadro number, just capital N. So now if we want to write this same equation, what will we have? Using the values that we got, we will get hydrogen gaseous form, and you supply 1313 kilojoule per mole, and you get ionized hydrogen gas. I'm waiting. If anybody has any doubt, let me know. Please look at the problem nicely. Okay, so if there is no doubt, let me go to the next problem. This is about the gyromagnetic ratio of an electron. Okay, so the gyromagnetic ratio of an electron revolving in a circular orbit of hydrogen atom is 8.8 into 10 raised to the power 10 coulomb per kgs. So what is the mass of the electron? And you have the charge of the electron mentioned. What is the gyromagnetic ratio? Yes, Dr. Jha, you are correct. Okay, so did anybody try to solve this? Okay, when we talk about, so the concept of gyromagnetic ratio, this originated from space quantization of electron movement, okay, or in an electron energy levels or whatever. Basically, they cannot, okay, I'll have to show you this. So basically, they cannot move in any direction they want. Whichever direction they will move, it is always discrete, it is not continuous. As long as the electron is in the vicinity of the nucleus, when it is in the when it is facing, an electric field which is originating from the nucleus, or it can also be due to the interaction of two side by side nuclei, and the other electrons around it. But of course, if you take the electron out, into the conduction band, where it's not where it does not feel the positive field from the nucleus, then of course this does not take place. Then these are just free electrons. But the minute they are in the vicinity of an atom, okay, which is not an ion or something, okay, basically in the vicinity of a nucleus of a positive charge, then it cannot behave freely. Every movement is discretized. Okay, so uh, if you have an electron, this is an electron, and this is the momentum, the angular momentum, okay, direction. So this, suppose it changes, okay, and this is the angle phi. This one is just the normal, and this is movement of the electron in some other direction. So its associated angular momentum, its magnetic moment, has also shifted. Okay, so say this is P, so P cos phi will be discrete, will be quantized, right? And from here we get the LZ term and all. But I'm just writing that this is quantized basically. This angle. So this is mk. And the electron is moving around this atom. So it has an associated magnetic moment. You calculate it as IA, right? So what is I? The electronic charge multiplied by the frequency, which is omega by 2 pi. and you have the area which is pi a square if this is a, the radius of the circle. So what does this give? E omega a square by 2. Okay, so this is the magnetic moment. Now the angular moment. So this is P, that will be, as you know, this is mvr. So in here r is a, the radius. So you have m omega and v is omega a. So m omega a square. Now the gyromagnetic ratio, gamma, is this magnetic moment divided by the angular momentum. So if you just divide these, you will get all these cancel out, E by 2m, okay, which is our gyromagnetic ratio. Now you put in the values. The charge is already given, 1.6 into 10 raised to the power minus 19, and the mass of the electron, it's 9.1 into 10 raised to the power minus 27 kgs. Let me just check. Sorry, 31. Okay, how much does that come out to be? Okay, what I have here is I'm so sorry, we have to find the mass of the electron. The gyromagnetic ratio is already given. Why is nobody, interacting? Looks like I'm solving it by myself. Okay, now you put M. Okay, and what I have here is 0.09 into 10 raised to the power minus 27 kg. So yeah, okay. So this is my answer. So question which follows, I hope this is okay. So the question which follows is, what is the magnetic moment of an electron when it is in the fourth orbit? N is equal to 4. Please think for a while and let me know. Okay, Dr. Jha. Four EH by 4PIN. Mm, let's solve it and let's see, because can you explain how you got that if you're comfortable? Okay, how do you pronounce your name, the one who just posted right now? Hmm. Okay, so yes, you have the magnetic moment as we had seen just here. Okay, here we did, okay, this one, yeah. Okay, magnetic moment is EVR by 2. Okay, and the angular momentum mvr is equal to nh by 2 pi quantized. Okay, so here n is equal to 4, right? Therefore mvr is equal to 2, put 4 here, 2h by pi, or VR is equal to 2h by m pi. Okay, so this is our number 2 equation. This is number 1. So now just put 2 in 1. Okay, so the magnetic moment is E by 2 2h by m pi. Okay, just cancel these and it comes out to be EH by m pi. Yes, so the one who had posted last haven't told me how you pronounce your name, so yes, that's correct. This is the answer. Okay, pretty straightforward. Okay, so we'll take a 5-minute break and we'll come back with this problem. Let me just show you the problem already while you can think about it. Okay, so we'll just take a 5-minute break. Okay, so I'm back. Uh, so yes, I've seen that somebody has already given an answer. Anurag, yes, you're absolutely correct. It's two. Why two? You if you have an elliptical orbit, so and you have an electron here, you have the radius changing, right? For an ellipse, you have A and B axis, and of course you have theta. So r and theta, these are the degrees of freedom. Sorry, these are the coordinates which can change. Okay, therefore the degrees of freedom is 2. What about a circle? The degrees of freedom here, yes, exactly. Again, I don't know how to pronounce the name. So yes, this, because here r is fixed, r never changes, so only 1 degree of freedom, right? Okay, one more. In this problem, what if I add, like I just really found a very nice concept that, let me write out the question for you. I didn't write it here. What is the magnetic moment? I'm just showing it like this, of an electron in a hydrogen atom in its first orbit. What will this be? Yes, again, the one whose name I can't pronounce is correct. So you have your, as usual, you have your moment is EVR by 2, and you have MVR is equal to NH by 2 pi. So for here, N is equal to 1, so just H by 2 pi, right? So therefore the moment is EH by 4 pi m. So what is this? Nothing but the Bohr magnet. Okay. So now I'll move on to the next problem. Can you calculate the linear momentum of an electron who is revolving in the first excited state of the hydrogen atom? Again, this is similar. Mind you, this problem has asked for the linear momentum and not the angular momentum. Dr. Jha says P is equal to H by 2 by R. Okay, but actually I was asking for the, like, if you can give me the expression, 1.054 into 10 raised to the power minus 34. Okay. Okay, so you have an electron revolving in just the first orbit, right? N is equal to 1 and K is also equal to 1. And the principal quantum number and the azimuthal quantum number, right? Which stands for S. Okay, so this electron is facing a centripetal force inside, right? So let us equate that. mv square by r is equal to the electric field. The centripetal force is due to the revolution of the electron around the nucleus, and the other one is just the electric field of the nucleus. E square by, okay, the force which the electron faces due to the, somebody wants to join. Okay, so the force due to the electric field of the nucleus. Okay, so from here we can write mv square is equal to now 1 by 4 pi epsilon 0. I will directly write the value 9 into 10 raised to the power 9. Okay, multiplied by e square by r. So this is my first equation. Now the angular momentum, which is discrete. So I know my angular momentum is quantized. mvr is equal to nh by 2 pi or nh cut, whichever you like. So let me number this as my second equation. So equation number 1 divided by equation number 2. Okay, this will give mv square by mvr, that is equal to 9 into 10 raised to the power 9 e square by r and 2 pi by nh. Okay, now n is equal to 2, so I will just write here 2h. Cancel. So let us put in the other values. Into e square 1.6 okay, so 1.6 10 raised to the power minus 19 using the bore radius. Okay, so if you put in the values, calculate all of this. You will get I'm sorry I missed the step here. mv square by mvr. We just put in these values 1 divided by 2 and this is v. Okay, from here. So this comes out to be 10.9 into 10 raised to the power 5 meters per second. So now linear momentum. MV So I'm getting something like 9.9 into 10 raised to the power 25 kg meter per second. Okay. So this is my answer. Dr. Jha says R is equal to 0.53 cross n square angstrom, where n is equal to 2. 0.5 0.12. Okay, Dr. Jha, I will see to that, and I'll edit my answer accordingly and upload it in the materials that are circulated. Okay, I'll just write that down. I'll try to include this. Okay. Okay, so now let us solve a few problems on the de Broglie wavelength of electrons. So you have an electron moving with the speed of 9.8 into 10 raised to the power 4 meters per second. So you calculate the de Broglie wavelength of the electron. So please try to solve it and let me know. Bintu Thomas said something. 7.43 nanometers. Okay. For this particular problem, I don't have the answer, so we have to solve it and check that. What about the others? Are you also getting the same answer? So what de Broglie said, this hypothesis, was that electrons, just like photons, electrons also have wave and particle nature. It can behave both as a particle and also as a wave. That means it has a dual character. Anurag has also got 7.42 nanometers. Okay, so maybe that's the correct one. Let's just see. So, okay, does this particular hypothesis apply to both macroscopic and microscopic particles, or is it only for microscopic particles? Can anybody just write that in the chat? Is this only for microscopic particles or both macro and microscopic particles? This particular de Broglie's hypothesis. Can anybody tell me that? Yes, this is both for macroscopic and microscopic. Okay. So according to de Broglie, wavelength is equal to h by mv, which is the momentum, rather the linear momentum of a particle, right? So from here, what is the wavelength of the electron mentioned? Let's see. We put in the value of h and mass of electron and the speed. So what does that come out to be? Let me just calculate. Oh, yes, it's correct. 7.422 into 10 raised to the power minus 9 meters. So that means 7.42 nanometers. So Anurag is closer. Okay. Now let us just solve this and see what, all this hypothesis uh, like if it can say tell us something interesting, and if we can relate it with real life examples. Okay, so you find the de Broglie wavelengths of a cricket ball and an electron. So let's see what the de Broglie wavelengths come out to be. Let me know. Anurag says B is 6.75 nanometers. Okay. Um, it's not exactly matching with the answer which I have. Okay, so probably you should check it somewhere. 0.728 nanometers. 0.07. Yes, that is closer to the one which I have. Right. Probably here Bintu gets the crown. But what about the first one? The cricket ball? What about the de Broglie wavelength of the cricket ball? Why is everybody interested in the electron only, not the cricket ball? Okay, so for the cricket ball, you find the de Broglie wavelength the exact way in which you found that for the electron. Because just as Anurag has said a few minutes before, that the de Broglie wavelength, sorry, the de Broglie hypothesis holds for both macroscopic and microscopic particles. And over here, the cricket ball is a macroscopic particle, right? So let us just use the formula we know, that is part A, lambda h by mv makes 6.6 10 raised to the power minus 34. Um, Dr. Jha, let's solve it. Okay, mass, it's already given, 200 grams. So let us convert it to kilograms. And the velocity, 5 meters per second. I'm not sure what units you have used, Dr. Jha, but I am converting this to kg per second. Okay, so for the velocity, I will be writing kg per. Okay, let me just write. The velocity is 5 meters per second. So how do you convert it to kgs per second? Because here I've converted this. So when that needs to be converted. Yes. But what I have here is something different. Why is that so? Okay, let's just solve it. Okay, so it's meters per second. Sorry, let's just go with that. Just 5 meters per second. So what does this give? 6.6 10 to the minus 34 divided by 200 times 3 divided by 5. Okay, I see why you got that, Dr. Jha. Yes, yes, even I'm getting that. Yes, I think it's okay. The solution which I have is different though. Okay, let's not bother about that. So yes, and for the electron, we have lambda is equal to h by mv. Just put in the value of electronic mass 31 and the velocity given 10 raised to the power 7 meters per second. So yes, what I have here is 7.3 10 raised to the power minus 11, which is it's better to write in nanometer form, 0.073 nanometers. So as you can see, just compare both of these. For the cricket ball, you have a wavelength which is very less, like it's extremely less, right? And for the electron, you have a wavelength which is, comparable to the dimension of atoms. Okay, so that is why we use the wave nature of electrons to study electrons and atoms. That is why we rely on the wave nature. Okay, but for a cricket ball, you can see it's 10 raised to the power minus 34 meters, which is like way off the order of dimensions of the cricket ball. So classical mechanics does not rely on, to study these. We don't rely on the wave nature. Okay, only quantum mechanics, only to study microscopic particles, we rely on the wave nature. Okay, so this is just a clear, conclusion that de Broglie wavelengths, de Broglie hypothesis is very well applicable. It can explain the electronic properties. Okay, so last one particular problem, let us just solve that. I just thought it's important. Yes. And I have to write it down. This is our problem number 10. Find the recoil speed of hydrogen atom after it emits a photon in going from n is equal to 3 to 1 state. Okay, and some constants are given. Take me as the mass of the electron and 1836 me as mass of hydrogen atom. Okay, and H and C, these are just the usual constants. So they have some options given, RH by C, RH by 205 ME, CRH by 2065.5 ME, and the last one R by 1205 cross HME. Here the H is in the denominator. So which one is it? Similar hydrogen atom problem. Somebody wants to join at almost 5 p.m. Okay, Okay, the class starts at 3 p.m., not 5 p.m. Okay, yes, so please just try to tell me what is this? Just the concept. Hmm. Okay, and what about the others? Okay, option C. Let me check. Yes, you're correct. Again, if you haven't told me how you pronounce your name, so yes, you're correct. Okay, uh, so this is problem similar to the hydrogen atom problems that we've solved, that the electron undergoes a transition from the n is equal to 3 to the n is equal to 1 state. But so we are going to use that same energy value, but here they want the recoil speed. So we just have to equate this with some v, okay, the velocity. That's it, nothing else. Okay, so I'm just writing it down that the energy of the hydrogen atom in the nth state, that's given by En is equal to minus RHC by n square. So therefore the energy required, I mean relevant to this transition, that will be minus RHC by 1 minus 1 by 3 square, which is n. Okay, so what does that give? So that's 8 by 9 RHC, isn't it? Okay. So now you have, so for this transition, there's this energy. That means a photon, if it would, I mean, if when the photon which is emitted, what is the momentum of that emitted photon? Okay. So the momentum of the n is equal to 3 and 1. So this electron is coming down and you have this photon. Recoil speed means, uh, suppose you have an electron just just sitting in its place, and you have something coming and hitting this electron. Okay, so this electron will go off in some other direction with some velocity v. This, you can say, this recoil or this bouncing back, or it was, originally sitting nicely, but it's suddenly been kicked. So this is just the recoil velocity, nothing else. The recoil speed. Okay. So now this hydrogen atom is just emitting a photon, right? So now the direction in which the photon will be released, this hydrogen atom recoil speed. Anyway, the recoil is just that, and it's usually in some other direction, in the opposite direction at which the force is coming. It's never in the same direction. Okay, so this the momentum of the emitted photon will be P is equal to del E by C. Okay, so that is just 8 by 9 RH. Okay, so V over here is the recoil velocity. So from the conservation of, okay, and one important concept I forgot to tell, that when there is a recoil speed or velocity, there is usually no loss of energy, as in we know, in like, just as in the form of heat, there is no loss like that. The energy is just distributed or taken by the bodies taking part in that particular event. For example, in Compton effect, the same happens. We'll be discussing about that in the later classes. So it's just that. So you see, conservation of momentum. Since it's a recoil speed, recoil velocity, so we can use the conservation of momentum concept here. So from this conservation of momentum, whatever, whatever is the momentum of this emitted photon, 8 by 9 RH. That will be equal to the mass of this hydrogen atom multiplied by its velocity. So basically, the momentum of the hydrogen atom, if it goes in some other direction, that will be equal to the momentum of the photon which is coming out due to the transition of the electron from the n is equal to 3 to the n is equal to 1 state. And so from here, if you plug in the values, you will get RH by 2065.5 mass of electron. And that's it. Okay. So from this problem itself, you can understand that the recoil speed of the hydrogen atom is like some, some reaction which has happened because of it emitting the photon. Okay, just some reaction movement. That's all. Okay, so we will end the class here. Thank you so much for joining. I will be uploading all of this, whatever we've solved, in the proper appropriate portals. So, okay, bye bye. I hope you have a nice evening. Thank you.
Thank you, ma'am.